Today, we will take a deep dive into the conceptual foundations of quantum mechanics, explore some of the core critiques against it, and introduce an alternative framework that may provide a more complete and intuitive understanding of physical reality. This approach integrates ideas from historical figures like Nikola Tesla and modern thinkers like Nassim Haramein, alongside other classical and field-based models. Our goal is not to discredit the enormous success of quantum mechanics in predicting experimental outcomes, but to challenge its philosophical assumptions and propose a more coherent, relational model of the universe. Let's start by addressing the fundamental issues with quantum mechanics, and then discuss how we can move toward a more holistic theory that incorporates field dynamics and continuous processes. Over-reliance on abstract mathematical formalism. Quantum mechanics is known for its heavy reliance on mathematical formalism, equations like the Schrödinger equation, matrices by Heisenberg, and complex probabilities that seem to disconnect from our intuitive grasp of the physical world. There is no doubt that the abstract mathematics of quantum theory has been remarkably successful in predicting experimental results. From the behavior of particles at subatomic levels to the energy levels of atoms, the math works exceptionally well. However, the concern here is that the success of the mathematics does not necessarily mean it reflects the underlying reality of the universe. What we've built in many cases are mathematical models that provide results but offer little intuitive or conceptual understanding of the physical processes involved. Consider David Bohm's pilot wave theory, which suggests that particles are not inherently probabilistic, but are instead guided by a deterministic wave. Bohm's theory uses the same mathematical predictions as quantum mechanics, but provides a clearer physical picture, one where particles have real trajectories, and randomness is replaced with hidden variables. Mathematical elegance alone should not determine the validity of a theory. If a theory disconnects from physical reality and intuitive understanding, it becomes challenging to expand into broader, real-world applications, like technology or energy production. This is one reason why field-based models, which we will discuss later, offer a more grounded alternative. The observer problem and the measurement issue. Now, let's talk about the role of the observer in quantum mechanics, a topic that has sparked debates for decades. According to the Copenhagen interpretation, the act of measurement causes the collapse of the wave function. In simpler terms, the reality we observe depends on us as observers. This famous thought experiment illustrates the oddity of this interpretation. Until observed, the cat in the box is considered both alive and dead, existing in a superposition of states. It's only when we open the box, when we observe, that the system collapses into one reality. The cat is either alive or dead. This observer-dependent reality raises serious philosophical concerns. Shouldn't the universe exist objectively, independently of whether we observe it or not? If we need observers to make reality real, we are veering into highly anthropocentric territory, something that's counterintuitive to the notion of an objective, consistent reality. An alternative view. The pilot wave theory sidesteps this problem entirely. In Bohmian mechanics, there's no need for wave function collapse or observer dependence. Particles are guided by an underlying wave, and measurement is just an interaction, not a trigger for reality to unfold. Field-based models like Tesla's ether or Haramein's vacuum energy take this further by proposing a dynamic field that governs all interactions. In these models, measurement is just another interaction between systems, not the defining element of reality. This restores objectivity to the universe, where systems behave deterministically, regardless of human observation. The non-locality puzzle and quantum entanglement. One of the most perplexing aspects of quantum mechanics is non-locality. In quantum entanglement, two particles that are entangled can instantly affect each other, even when separated by vast distances. This phenomenon has been experimentally verified, but it directly challenges classical notions of space, time, and causality. If particles can affect each other instantly, regardless of distance, then either information is traveling faster than light, which violates relativity, or there's something deeper we don't yet understand about the nature of space and time. Einstein himself called this spooky action at a distance, and was deeply uncomfortable with it, because it suggested a breakdown of local realism, the idea that things happen in a localized, predictable manner. An alternative explanation, waves in a continuous field. If we take a step back and consider the universe as fundamentally wave-based or field-based, then non-locality could be explained by wave interactions in a medium. Think of it this way. In a continuous medium, like the ether or the fabric of vacuum energy, waves can propagate and influence each other over large distances. The entanglement of particles might not be a mystical connection, but an effect of waves interacting across this medium. This brings us closer to classical ideas, where things operate continuously and predictably, and it aligns with Haramein's concepts of an interconnected vacuum field that governs particle interactions, even at great distances. At the heart of quantum mechanics is the notion that energy is quantized, existing in discrete packets, or quanta. Yet many processes in nature appear to be continuous. This raises questions about the true nature of energy. According to quantum theory, energy levels in atoms, for instance, are discrete. We see this in the form of spectral lines, clear evidence of specific energy jumps. But what if these jumps don't reflect intrinsic chunks of energy, but instead stable vibrational patterns? Tesla's vision of the ether and Haramein's vacuum energy suggest a different picture. In their models, what we observe as quantized energy levels could be the result of standing waves or stable vibrations in a continuous field. Think of it like the harmonic frequencies of a musical instrument. The notes are distinct, but they arise from the natural behavior of the string or air column in continuous motion. This perspective offers a smooth, continuous model of energy, where what we see as quanta are just points of stability in a field. This not only aligns with our everyday experience of continuous processes, but also eliminates the need to think of energy as inherently quantized. Quantum mechanics often treats particles, electrons, photons, etc., as fundamental, indivisible entities with fixed properties. However, critics argue that particles may not be fundamental, but are instead theoretical constructs that emerge from our models. Quantum mechanics grapples with the duality that particles like electrons sometimes behave as waves and other times as particles. This duality is a cornerstone of the theory, yet it introduces a conceptual divide that is difficult to reconcile. What if particles are not fundamental at all? In a field-based universe, particles might just be localized excitations or disturbances in the field. This would make all of reality fundamentally wave-like, with what we call particles being emergent phenomena. This was Tesla's view, and it aligns with de Broglie's pilot wave theory. One of the most profound shifts quantum mechanics introduced is the idea of indeterminism, where probabilities, rather than definite causes, govern the universe. However, this shift away from causality has left many physicists uncomfortable, including Einstein. In quantum mechanics, the behavior of particles at small scales is inherently probabilistic. We can't predict exactly where an electron will be, only the probability of its location. While this works mathematically, it undermines the classical idea that the universe operates according to fixed causes and effects. In both pilot wave theory and field-based models like Haramein's vacuum energy, causality is restored. Waves or fields move in predictable patterns, and particles, if they exist as localized phenomena, follow deterministic trajectories. This return to determinism not only satisfies the need for logical consistency, but also provides a clearer pathway to technological applications, like Tesla's dream of tapping into the ether for unlimited energy. One of the most exciting aspects of the alternative, field-based models, those proposed by Nikola Tesla and expanded upon by Nassim Haramein, is the potential for real-world technological applications. While quantum mechanics has led to important technological advances like semiconductors, lasers, and quantum computing, its fundamental framework does not seem to offer a direct path toward the revolutionary energy sources and technologies that thinkers like Tesla envisioned. Let's explore these possibilities in more detail. Nikola Tesla famously believed that the ether, a medium once thought to permeate space, could be harnessed to provide free, wireless energy to the entire planet. He envisioned a world where energy could be tapped directly from the environment, and power could be transmitted through the atmosphere without the need for wires or physical infrastructure. Tesla's experiments with wireless energy transfer, particularly through his famous Wardenclyffe Tower, were aimed at demonstrating that energy could be broadcast over great distances by resonating with the natural electromagnetic frequencies of the Earth. Though his project was never completed, Tesla was convinced that the ether, or some equivalent underlying field, held vast stores of energy potential that humanity could harness. Tesla believed that space itself, filled with dynamic energy, could serve as an endless reservoir of power. He saw the Earth as a giant conductor, capable of tapping into this latent energy, much like a machine could tap into the flow of electricity. His vision was based on the assumption that the universe is filled with vibrational energy, and that by accessing the correct frequencies, we could unlock this power source. Building on Tesla's ideas, Nassim Haramein introduced a concept known as vacuum energy, suggesting that space itself is not empty, but filled with an energetic field that vibrates at the Planck scale. This energy, though not yet fully understood, could potentially be harnessed for practical uses. Haramein argues that the so-called vacuum is actually a rich sea of energy, and by interacting with the vibrational dynamics of space at a fundamental level, we could extract and use this energy. Zero-point energy is a key concept in both mainstream physics and alternative models like Haramein's. The idea of zero-point energy comes from quantum mechanics, which suggests that even in a vacuum, there is residual energy that can never be completely removed. While quantum mechanics sees this energy as largely inaccessible, Haramein's framework suggests that with the right understanding of the geometry of space, this energy could be tapped and utilized for technological purposes. If vacuum energy or the ether is filled with dynamic vibrational energy, and if we can access and control this energy, it could lead to breakthroughs in energy generation, enabling sustainable, unlimited power that doesn't rely on fossil fuels or traditional energy sources. This has enormous implications for global energy supply, potentially solving many of the planet's energy problems and reducing our reliance on polluting technologies. Quantum mechanics, despite its tremendous successes in specific domains, does not inherently offer a path to harnessing such energy on a practical level. Quantum field theory predicts the existence of vacuum energy, but the mainstream interpretation treats this energy as unusable. It remains locked in mathematical abstractions rather than offering a direct technological application. In the quantum paradigm, the energy of the vacuum is seen as a byproduct of fluctuating fields, but these fluctuations are not typically considered accessible for technological use. Even though quantum mechanics accurately describes the behavior of subatomic particles and energy at very small scales, it doesn't provide the tools to turn the theoretical zero-point energy into a usable resource. In contrast, both Tesla's ether theory and Haramein's vacuum energy suggest that this hidden energy can be accessed and manipulated through resonance, vibration, and geometric configurations. These field-based models open the door to possibilities like wireless power transmission, clean energy technologies, and even gravitational control, which quantum mechanics does not currently address. Moving from theory to practical application, the key challenge lies in engineering the tools to interact with the underlying field of space, whether it's Tesla's ether or Haramein's vacuum energy. Both envision a future where energy flows freely, where electromagnetic fields, vibrations, and geometric structures can be tuned to resonate with the fundamental frequencies of the universe, thereby unlocking limitless energy. In Tesla's wireless energy experiments, the Earth itself was seen as a key player, a conductor of energy that resonates with the frequencies of the atmosphere and space. By tapping into this natural resonance, Tesla believed we could transmit energy over great distances. Haramein's focus on the geometry of space expands on this by proposing that resonance at the quantum vacuum level could similarly allow us to access and utilize this energy. If successful, field-based energy technology could lead to new power systems that are environmentally friendly, sustainable, and provide global access to energy. It could also revolutionize other areas of technology, from transportation to communications, possibly even enabling concepts like anti-gravity or faster-than-light communication through manipulation of the underlying field of space. In sum, both Tesla's and Haramein's ideas push the boundaries of what is possible by exploring the latent energy hidden in space itself. While quantum mechanics offers a deep mathematical understanding of the microscopic world, it stops short of providing a framework for tapping into this vast potential energy source. Field-based models, on the other hand, envision a universe rich with vibrational energy, waiting to be harnessed. If these ideas can be developed further into practical technologies, the implications are transformative. The world of free energy, once relegated to science fiction, could become a reality, providing humanity with the means to solve some of its greatest challenges: sustainable energy, environmental conservation, and equitable access to resources. With continued research and exploration of field-based physics, we may one day find ourselves living in the world that Tesla and Haramein envisioned, a world where energy flows freely from the very fabric of the cosmos itself. Bringing it all together, a unified field model. As we approach the conclusion of our exploration, it's crucial to recognize that the critique of quantum mechanics we've discussed does not diminish its success in predictive experiments. Instead, it addresses the philosophical and physical gaps left by the current quantum paradigm. What we are proposing is not just a critique, but a reconceptualization, an alternative framework that unites the strengths of both classical and quantum ideas through a field-based, continuous, and deterministic model. At the heart of this reimagined framework lies a more unified vision of the universe, which replaces the quantum world's abstract, probabilistic nature with a continuous and interconnected model of reality. This approach aligns with many classical thinkers' ideas while embracing the discoveries and advancements in modern physics, but reframes them in a more intuitively coherent way. Instead of discrete particles or quanta, we emphasize the idea that what we observe as particles or quantized energy is the result of stable vibrational patterns in a continuous medium. Whether we call this medium the ether, vacuum energy, or something else, it underlies all observable phenomena, allowing for a seamless transition between wave-like and particle-like behaviors. Unlike the randomness inherent in quantum mechanics, the field-based model restores determinism. Each interaction in the field follows predictable causal patterns, akin to the way waves interact in classical systems. This makes the universe more intelligible and opens the door to new technological breakthroughs. Instead of particles affecting each other instantaneously across vast distances, as in quantum entanglement, non-locality can be understood as wave interference across the continuous field. This eliminates the need for spooky action and provides a more intuitive explanation of how distant systems remain connected. The collapse of the wave function and the role of the observer in quantum mechanics can be replaced by a model where observation is just another interaction within the field. Reality exists objectively, independent of observation, with systems continuing to function deterministically as part of a larger whole. Technological and philosophical implications. One of the most exciting possibilities with a field-based approach is the potential for new energy sources. If the universe is indeed filled with dynamic vacuum energy or a similar continuous medium, as Nassim Haramein and Nikola Tesla proposed, then the prospect of tapping into this universal field for energy could revolutionize technology, providing abundant, sustainable, and possibly even wireless energy. Philosophically, this shift from quantum indeterminacy and abstraction to field-based determinism and continuity presents a more intuitive and cohesive picture of the universe. It also brings back the idea that cause and effect rule at the most fundamental levels of nature, aligning with the deep human drive to understand reality in terms of order and reason. In conclusion, we stand at a critical juncture in the development of modern physics. The quantum model, while incredibly successful in certain respects, leaves many foundational questions unanswered. By drawing from both historical wisdom and emerging ideas like Tesla's ether, Bohm's pilot wave theory, and Haramein's vacuum energy, we can begin to construct a more holistic model, one that addresses the shortcomings of quantum mechanics while offering a clearer, more intuitive understanding of the universe. This field-based model not only resolves many of the philosophical concerns, such as the role of the observer, non-locality, and the nature of particles, but also provides the conceptual and practical tools needed to push forward into a new era of technological innovation. From free energy to wireless transmission and beyond, the potential applications of this paradigm shift are profound. Ultimately, by embracing continuity, causality, and interconnectedness, we are not just building a new theory. We are setting the stage for a broader, more integrative understanding of reality itself, one that is rooted in the principles of balance, vibration, and field dynamics, and that promises to unlock new levels of insight into both the microcosm and the macrocosm of our universe. Thank you for your attention and your open-mindedness. Together, we can continue to explore and refine these ideas, pushing the boundaries of our understanding as we move toward a more comprehensive and unified picture of the cosmos.